Good morning. Today my lecture is torque equation. Okay, torque equation. How to measure the torque value in three-phase induction machine. Okay, that we are going to discuss it by today. Step-by-step procedure. Okay, step-by-step procedure. So generally, we know that if you take a DC motor, okay, if you take it in DC motor, if you take it DC motor, the electric power is conducted directly through armature and brushes. So in DC motor, the torque value, okay, the torque value is directly proportional to flux and product of flux and armature current T is directly proportional to phi into Ia, where T is the torque and phi is the flux per pole. Okay, T is the torque, phi is the flux per pole, and Ia is the armature current. Okay, so in DC motor, the torque is directly proportional to flux phi into armature current, product of flux and armature current. Likewise, in induction motor also, induction motor means it will be a AC motor. Okay, induction motor also, the torque is directly proportional to product of flux of stator pole and rotor current. That is, phi is nothing but flux per stator pole, and I2 is the rotor current. Okay, rotor current. So here what happened, we are giving the input like a three-phase AC supply. So normally if you give three-phase AC supply RYB, a rotating magnetic field is produced. With respect to the, it will be called degree. Okay, it will be the time, the overall degree is 360 degree. So we have to consider the power factor also. Okay, cos phi 2. Okay, cos phi 2 is the power factor. Okay, cos phi 2 is the power factor. Okay, so torque is directly proportional to flux per stator pole and rotor current I2 and power factor. Okay, T is directly proportional to phi I2 cos phi 2. What happens in DC? In DC, this phi 2 is 0. So here cos phi is 0. Cos 0 will be 1. So T is directly proportional to phi into Ia. So that the power factor is unity. Okay, in DC motor. But in DC motor, the torque is directly proportional to product of flux per stator pole, rotor current and power factor. Now if you take this direct proportional symbol T equal to, if you take this proportional symbol, you will get a constant K into phi into I2 cos phi 2, okay, into cos phi 2. So where K is nothing but constant, okay, K is nothing but constant, denoting now the rotor EMF at standstill. That is, it's not running it. Okay, it's not running it at standstill by E2. Okay, by E2. So we have E2 is the rotor EMF. E2 is directly proportional to phi. E2 is directly proportional to phi. Okay. Now this equation, this T equal to K phi I2, you mark it as equation number 1. Okay. You mark it as equation number 1. Now substitute the value of E2 in equation 1. Okay, equation 1. What is the value of E2? That is nothing but phi. Okay, so T equal to K into, instead of phi we have to substitute E2. T equal to K into E2 I2 cos phi 2. Okay, T equal to K into E2 I2 cos phi 2. Since we are substituting, instead of phi we are substituting E2, so the constant parameter also be changes. Okay, that is K1. Okay, where K1 is the another constant. K1 is the another constant. Okay, K1 is the another constant. So your equation is T equal to K1 into E2 I2 cos K into E2 I2 cos phi 2. Okay, this equation is called it as relation between torque and power factor. Okay, this equation is called torque and power factor. This is one 3-mark question. Okay, 3-mark question in your examination. Okay, so in DC motor, again I will explain. In DC motor, the torque is directly proportional to product of flux per pole and armature current. Okay, but in AC motor, the torque is directly proportional to product of flux per stator, because flux will be induced in stator. Okay, first flux will be induced in stator. So flux per stator pole and rotor current and power factor. Okay, power factor. Okay, now if you take this direct proportional symbol T equal to K, you will get a constant K into I into cos phi 2. Now you mark it as 1. Okay, the condition. Now the rotor not running, it will be in standstill position. So in standstill position, the flux is directly proportional to rotor EMF. Okay, E2 is nothing but rotor EMF. E2 is rotor EMF at standstill. EMF per phase at standstill. Now substitute instead of phi, please substitute E2 in above equation, in equation 1. So you will get T1 equal to K1 into E2 I2 cos phi 2. So this K1 is, we will get another constant. Okay. So this equation call it as the relationship between torque and power factor. So from that what you are understanding, if you are increasing the rotor EMF, if the rotor EMF increases, the rotor current is also increases, automatically the torque value will be increases. Okay, it will be increases. Suppose if your rotor current, okay, if your rotor current decreases and cos power phi 2, that is power factor is also be decreases. Once power factor decreases, then torque value will be decreases. Okay, torque value will be decreases. Are you understand my point? That is, if power factor, okay, if power factor means cos phi 2, power factor increases, then torque also be increases. If power factor decreases, then automatically the torque value will be decreases. Okay, torque value will be decreases. This is one more question. Okay, if power factor increased in 3-phase induction motor, what happened to the torque? Immediately you have to write increases. If power factor decreases, torque will be decreases. Torque will be decreases. Okay, then another. Now we are going to measure how to calculate the starting torque of 3-phase induction motor. Okay, 3-phase induction motor. Starting torque of 3-phase induction motor. What does mean by a starting torque? The torque developed by the motor at an instant of starting. Okay, the torque developed, I will write the torque developed by the motor at the instant of starting is known as starting torque. The symbol for starting torque is capital T suffix small st. Okay, capital T small st. And when we are going to measure this starting torque means during rotor at standstill. Okay, standstill means it's not running it. Okay, during rotor at standstill, we have to calculate starting torque. Okay, TST. We have to calculate starting torque TST. Okay, now we know the basic equation. Okay, right, we know the basic equation of torque and power factor. Okay, what is the basic equation? T equal to K1 into E2 I2 cos phi 2. Okay, T equal to K1 into E2 I2 cos phi 2. Okay, now we have to substitute the E2 value, I2 value. Okay, we know the what is the meaning of E2? E2 means rotor EMF per phase at standstill. And I2 is the rotor current per phase at standstill. And cos phi 2 is the rotor power factor. Rotor power factor at standstill. Okay, yesterday class I explained what are the how to find out this E2 value, I2 value, power factor value during a standstill condition. Now we will just recollect it. Okay, just we will recollect it. And now we are going to calculate the I2. Okay, rotor current. Rotor current means during standstill condition, what is the rotor current? I2 equal to E2 by Z2. So E2 equal divided by Z2 value, we know the magnitude of impedance, square root of R2 square plus X2 square. Okay, this is the I2 equation. Okay, this is the I2 and power factor also. Cos phi 2. Cos phi 2 will be, how to calculate cos phi 2? By using the impedance triangle, right angle triangle. Okay, this is phi 2 R2 reactance X2, this is impedance R2 X2 Z2. So cos phi 2 will be adjacent divided by hypothesis, that is R2 by Z2. So R2 divided by Z2, what it is? Magnitude of impedance R2 square plus X2 square. R2 square plus X2 square. Okay. Now substitute substitute I2 and cos phi 2 in starting torque equation. We get, what is the starting torque equation? TST is equal to K1 E2 I2 cos phi 2. This is starting. Now substitute the value. K1 into E2. What is the E2 value? E2 we don't know. Okay. E2 you put it as it is because here rotor induced EMF. Into I2 value. What is I2? I2 will be E2 divided by square root of R2 square plus X2 square into cos phi 2. How much? Cos phi 2 is R2 by square root of R2 square plus X2 square. Okay, now again K1 into E2 into E2, you will get E2 square, okay, into R2 divided by square root of R2 square plus X2 square into square root of R2 square plus X2 square. You will get R2 square plus X2 square. Okay, R2 square plus X2 square. So this K1, okay, K1 substitute K1 is a constant because we know K1 is a constant. Substitute K1 equal to how many phases which we are giving to our induction motor? 3 phase. So 3 phase divided by how much angle it is? The one cycle will be, this is pi, this is 2 pi. So one cycle is 360 degree. So 2 pi into synchronous speed. Okay, we know ns is synchronous speed. Okay, so substitute this value. This is my equation 1. Substitute K1 value in equation 1. Okay, K1 in equation 1. So therefore starting torque TST equal to 3 by 2 pi ns into E2 square R2 divided by R2 square plus X2 square. This is the starting torque equation. Okay, this equation is known as starting torque equation. Okay, this equation is known as starting torque equation. Suppose, note, suppose if supply voltage V is constant. Okay, is supply voltage V is constant, then the flux phi and rotor EMF are both are constants. Both are constant. Therefore, TST equal to, you get 3 by 2 pi ns into this E2 square. What we'll do? E2 square we should not put it because it is a constant. Okay. So this constant parameter will get, it will be unity. So R2 by R2 square plus X2 square, or in another case we can write it, TST is equal to K1 into this E2 square, we can write it as K constant R2 by R2 square plus X2 square. So therefore starting torque, because there are two constants, so we can mention the new constant called K2 into R2 by K into R2 by R2 square plus X2 square. Okay, this is the starting torque equation for if supply voltage V is constant. Okay, if supply voltage V is constant. Till now you have any doubts? Tell me.
So when we are substituting the value of K1, how we are getting that 3 constant? Can you explain it again?
Actually, K value will be the constant because in our three-phase line, this is the stator, this is the stator. Okay, here only windings are there. Okay, this is the stator. Inside only rotor is there. This is the rotor. Now in stator we are giving three phase RYB. This RYB called as three phase line. It should be a unity, it should be balanced line. Okay, so this balanced should be a constant value. Okay, that you should not vary, because if the balanced line will be vary, automatically the motor will go to damage condition. That's what we are saying, that is a constant parameters. That is your 3. Okay, 3 value. 3 is nothing but number of phases. How many phases we are operating it, divided by this 3-phase line will be operated by 360 degree RYB. Okay, each phase is 120, 120, 120. So total if we add it will be 360 degree. That is 2 pi. 2 pi into, if we give 3-phase line, the current flows in the stator. So during that time the rotating magnetic field, that is rotating magnetic field means flux is produced. In the flux only we are setting the ns, synchronous speed. Okay, synchronous speed, that is your denominator. Okay, so this 3 by 2 pi ns will be a constant parameter which will be set by the manufacturer. Okay, not by us. Okay, we are not setting this 3 by 2 pi ns. But if we give this 3 by 2 pi ns, then only we can measure the speed, rotor speed across the shaft. Rotor speed across the shaft. If the rotor speed will be produced, automatically the torque is produced. Okay, so this is the concept. Are you got my point, Anirudh? 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 Do you have any doubts?
No, sir. No.
Okay. Okay. So, in this lecture, you have understood the concept, the torque, the relationship between torque and power factor. In DC motor, the power factor is unity. It will be 1. So, you will get only T is directly proportional to phi into Ia. But in AC motor, the power factor will be variable. It will be variable. It will be lagging as well as leading based upon the winding, because the winding will be a inductance. Okay, it will be inductance. It is having a lagging as well as a leading based upon the load also. So that's what we are getting. Torque is directly proportional to flux per stator and rotor current and power factor cos phi 2. So by using this basic equation, we are measuring the starting torque. What is the meaning of starting torque? The torque developed by the motor at the instant of starting is known as starting torque. And this starting torque at the instant of starting means it will be in standstill condition. That's what the notation is, TST. Okay, maybe you understand this derivation. This is one 10-mark question in your examination. So next hour, that is in hour number 2, I will explain how to measure this starting torque in screw gauge motor and slip ring motor, and then I will explain about the running torque also.